Hello everybody and welcome to another class. Day 2 of our series of CS 219. So what are we going to cover today? We are going to be covering from sections 1.3 to, I suppose, hopefully 1.6, but we shall see. Basically, we left off last time talking about cache, right? And we were doing a bit of an example. We didn't quite talk about cache, but we were trying to introduce cache by giving you an example. You know, 11:20 wouldn't be so bad. This is a rough time for me in the morning to teach a class, so yes. But so be it. So anyways, so the example that we were going to talk, that we were kind of talking about, was the concept of, is electricity too slow for our purposes? And the short answer is yes. We are limited in computing by the speed of light, because that's also the speed of electricity, because it's the flow of electrons per se, and that is actually too slow for some of our computers, because when you have a very fast clock rate or clock cycle, which we'll get to talk about in just a little bit, essentially it means that you can do X amount of operations in a second, and it turns out that you can go faster than the time it takes to communicate between your computer and main memory, where you have to store the data that you're working on. And so one of the ways around that issue is to bring the memory closer to the CPU physically, so that you can shorten that distance. And by shortening the distance, you can speed it up. So I actually went on and Googled last night, probably at like 4 in the morning, some kind of comparisons. And while this isn't exactly, I would say, scientific, or not 100% sure if it's right, it seems kind of right. So I'm going to go ahead and show it. So that would be here. So this is somebody. So this is numbers from Jeff Dean, research Google people, and a graph by Thomas Lee. And again, they just found this literally on Google as I was trying to Google some comparisons of things. And the one that I usually remember, which here would show up under, I suppose, right around here, yeah, is, it takes 1 millisecond to be able to, well, here they say it takes 10 milliseconds, but I thought it was 1. But it takes, in this case, they say 10 milliseconds, even though I think it's 1, to read something from your hard drive. Okay, and that's just simply to find it in the hard drive. And we will talk about seek time and things like that when we get to that. But that's pretty slow. And so most of you know that the reason we came up with random access memory, which is RAM, your main memory, is because it's a lot faster to read and write than your your hard drive, right? And so the question was, is that the fastest that we can achieve? And it turns out that RAM itself is not as fast as either, because here you have somebody saying that accessing something from main memory takes 100 nanoseconds. Okay. Now we computed ourselves that just the distance to get to the memory from the CPU takes us 0.16 of a nanosecond, right? So I guess you gotta add that into that. But I thought, frankly, that it was faster than that. But even then, you can see that accessing something from main memory taking 100 nanoseconds is a lot slower than a CPU that can handle sometimes more than 1 operation per nanosecond. And I do believe you guys last time on the chat, I can actually open up my recording of the chat here, and somebody said that they Googled that it took at least 3 washing machines per second. No, somebody said that they found that the fastest computer was, I think, the fastest clock cycle was 1 to the -12. So that would be even smaller than a nanosecond. It would be, I think, a picosecond, because nanosecond, I believe, is 10 to the negative 9th. And then from there you have another unit, and then you have millisecond. That middle unit, I can't remember the name. But we can, find it in metric units per second. That one Wikipedia article that we looked at last time. That's going up is deca, hecta, kilo, omega. That's up, but now we need to go down. Where was it? I can't remember. You guys find it on chat and then let me know what the one in between seconds and nanoseconds are. So go ahead and figure that one out. But anyways, so this is pretty slow. And so one of the ways to speed it up is by putting faster memory that is actually closer to the GPU. And then you can achieve something closer to the same speed that you can do a clock cycle. And so here you can see that they're talking about Mutex. Mutex is actually related to concurrent programming and the potential hazards that you come up with that. I don't think that's something that I talk about in this class. They will talk about it in somebody find the link to the scale of all the seconds, like nanosecond, millisecond. I posted it last time. Orders of magnitude. Yeah, that sounds about right. Thank you. So this should be the right article here. So here we go. So we got microsecond. That's the one in between. That's the one that I couldn't remember. Yeah. So you go from second, millisecond being 1,000th, and then if you go 1,000th of that, you get to microsecond, which is the one I could remember. Then you get to nanosecond, and then even smaller than nanosecond is going to be picosecond. So every 3 extra zeros, over. And so, yeah, and that, that's kind of the opposite of like when we think of like bytes and size of things. They go from kilo to mega to giga to tera and then to peta, which I think is about the size that we, we're dealing with nowadays. But yeah, on the way down, that was the one I covered, microsecond. So yeah, so essentially, with Mutex, because it's a 370 subject, we don't talk much about it. But the way it works is, if you have 2 programs, because we did mention that we might have a multi-core computer, right? You have 2 cores, and those cores are both trying to work on the same data. So imagine the data is on a shared register, okay? Because it probably is. And so that data, is a counter. And suppose that both of these things are supposed to be increasing the counter by 10 times each, okay? Ideally, because they're supposed to increase it 10 times each, you want to have the final result to be 20 here, okay? But if I am increasing it at the same exact time because they're running in parallel, so because you're trying to do that computation, they may both try to go in at the same time and change it. And what can happen there is, how do they increase a counter? What they have to do is, first they have to look in the register and see what the number is. So let's say they see they have there's a 6 in there, okay? And then they look at that 6, they add 1 to that because they use their arithmetic logic unit to increase 1 to 6, which they get 7. And then they go in and write it, right? So it's like, I'm here, I look over here, and I'm like, okay, there's a 6 in there. Okay, let me grab that 6. All right, let me do my computation. 6 plus 1 is 7. Cool. And then I go back and I put it in there. Okay? Well, guess what? In the process of you taking the old number, computing the answer, and then coming back and putting it in there, and even something as simple as plus 1, in the meantime that happens, the other person or the other core is doing the exact same thing. And so what you get there is a race condition in which both things, they both look at the 6, they both grab the 6, they both increase it by 1, and then one of you is going to come back and put a 7, and then it's going to get overridden by somebody else putting 7. And so when you should have increased by 2, then you actually ended up increasing by 1. Or worse yet, suppose that 1 is like slower. So this guy gets a 6, he's reading the 6, and now he's going to be adding 1 to that, and then he's going to come back with a 7. But in the meantime, the other core grab the 6 that was there, increase 1, put a 7 there. Then grab it actually again and put an 8. Then grab it again and put a 9. Then grab it again and put a 10. And then he's doing other things. And you're still coming back here with your 7. And then you just put it over completely. And bam, you just overwrite it. And so that's a problem. And so one of the ways that you can avoid that is with a mutex, which you can think of it like a little semaphore. And so a semaphore, is like when you're driving in the street, a traffic light, a red light or a green light. And so if you go and you're gonna update this value, before you touch it, you're gonna look at a semaphore. If the light is green, then you are okay to grab it. But before you grab it, what you're gonna do is you're gonna put the light to red, and then you're gonna go and grab the data. And then that red light means that if somebody else comes and wants to update the data there, they can't even look at it. They have to wait for the red light to turn green. Even if you take forever, like, oh yeah, I'm changing the data here, and I'll come back with the new data and put it in there. Even if it takes you forever for that, the other guy's just gonna have to sit there and wait. And then once you update the data, first you update the data, then you go and you tell the semaphore, okay, switch to green, and bam, it switches to green. And that's one of the many ways that you can solve a race condition, but that involves special instructions in your architecture actually to implement that, because otherwise you have the exact same problem that you had on the variable you can have on the semaphore, where imagine that two processes or two cores come in and they both see the green light and they both turn it red at the same time. So you can have the exact same issue you had with the variable, you could have with the semaphore actually. And so while this might seem like an elegant solution, it's not. It will not work unless that the semaphore itself is done with a special instruction that controls that situation by not allowing two things to change it at the same time, which is actually how it works. And so that's why that actually is a useful solution, and you can't just code your own semaphore per se. Are you really getting PTSD from 218? Like, did they cover semaphores in that? That's actually hardcore if they did. So, yeah. Damn, that's hardcore. So anyways, there's, in 370, that's like a quarter of the class is talking about ways to solve race conditions. So that's why this might be the only time you ever hear about that. But anyways, the process of turning the light from red to green takes time. And in this case, they're saying it takes about 25 nanoseconds. So that's going to slow your program down, right? So, you might be like, oh, I'm going to put semaphores for all my variables because I want to be super safe for, for race conditions. Yeah, that's not good because it's going to make your program slow. So you really only want to do it in the ones that actually can potentially have a race condition on them. So anyways, that's what that means by the mutex lock unlock. And then the cache is that, what I want to talk about. But as you can see, look at the speed of the cache. The cache reference. So accessing the cache is so much more faster than accessing your main memory by a factor of almost, if 200 technically, from 0.5 to 100. Oh yeah, here you can see the scale, the rate, So even from well, it's harder to see from this because the math might be easier to see it here. But here would be a factor of like 12 from L2 to main mutex, whereas here's a factor of 4. So here they put a scale to better understand speed-wise how big of a difference there is between, like, say, 5 nanoseconds and 20,000 nanoseconds by making the scale be 1 second. And they're like, imagine that an L1 cache takes 1 second to run. How slow is memory compared to your cache? Well, if it took 1 second, main memory would take 3.3 seconds. And then if you read something from your hard drive, it would take 7.7 months. Okay, or for the internet, sending something via Ethernet cable back to the servers or whatever, and then through the internet will take years. So it's a big difference. And so we want to be as close to the speed of the CPU because that's going to be the fastest part, and we don't want to have that be hampered down by the other components. And you will see that a lot of the things we talk about this class when we talk about pipelining and then caching are strictly made to not have the CPU waste time, because the CPU is like super smart. You want to make sure you use him 100% to his power, right? To his potential. And the only way you can do that is by always having things ready for him to run. If he's just sitting there waiting, that's just a waste of resources. So that's usually what we work the technology around, the CPU, to be able to take advantage of its power to the max. Because that's, it's an expensive part of the computer too. It's probably the most expensive part of the computer, if I was to guess. If you get like Yeah, I mean, maybe the GPU is pretty expensive too, though. So, but that's kind of another processing unit in a way. So, anyways, how does cache work? Well, we are going to be spending, I think, a chapter or more on caching itself, but the basics are simple. It's a different kind of memory, and it is actually located very close to the machine CPU. Let me see if let me switch over to that. Okay, so what you're looking at is a close-up of an actual CPU chip. Okay, so like, you know, those little chips, the one that you put in your computer, that's in the motherboard. This is a close-up of that, and this is from the book, but you know, bigger here, easier to see. In this case, this is actually a multi-core machine. It's an a Z13 processor, and there's also here a core layout of individual cores. So this, we're just looking at all of the cores, and you see here that they say L3, and which are the ones here we have? Yeah, just L3s. And then on this one, an individual one, then there should be more. So here, let me open the book so I can remember some of these acronyms mean. But ultimately, if you go in and look in something like this, which is kind of the diagram version of that, you can see that there is a shared cache between the different processors. I made a mistake there. Between the different processing units, because the processor in this case is the entire thing, right? Remember, that's the thing I said last time that it's kind of confusing in the book. So processor is the entire chip. Processing unit or core, interchangeable, those two are the individual cores. Okay, so in this case, they all in this 8-core chip share 2 caches, and notice that it says L3. The reason why is because we call different caches different levels. So we got level 1, level 2, and level 3. Okay, so this is, you know, basically the level 1, the lowest level, is going to be the one that's closest to the CPU, and that's going to be the the fastest type of memory that you could have. Okay, that is going to be the state-of-the-art memory, and super close to the actual arithmetic logic unit and the control unit and all of those pieces of the CPU that actually require to have data as close as possible to them. Okay, that's going to be your L1 cache. Because this is very expensive memory, and because you have very limited by the space that you can have inside a chip, typically you don't have a lot of it. In a second here, when we not a second, but a little bit, when we get to, I don't know, it was later on in the reading, like 1.4. They actually have a history of all of the processors, and they kind of talk about the different sizes of these and how they went. But like looking just here at a modern computer, the L3 cache, which is the one that's furthest away, is 14 megabytes. And typically you can see the L2 cache being around 2 megabytes. And then the L1 cache is around the kilobyte range, probably, if I was to guess. But usually, this is actually a popular enough thing that when you go and buy a computer, they actually advertise this thing sometimes. Which I'm surprised, because usually people are confused about why they have this megabyte size memory thing. And they're like, I want a gigabyte in my memory. And they're like, you know what? They have no idea what they're talking about, because this is cache. So yeah, L3 cache is going to be the biggest one because it's the furthest away. And in this case, it's actually shared between cores. So if cores need to communicate to perform operations, L3 cache is going to be for them. And in the case of something like a modern CPU, it's about 15 megabytes. If you got 2 of them, it's probably split into two 8 megabyte pieces or something. And so inside of each core, though, then you have the L1 and L2, level 1 and level 2 caches. And notice that you have 2 types. You have, this might be kind of tiny, but there's a data cache and there's an instruction cache. We got some questions here. So is the reason cache is so much faster than RAM mainly just distance has to travel? No, there are other factors. Distance is one of them, yes, but there are other factors. The type of memory that is done in RAM versus the type of memory that is done in cache is a little bit different. RAM is random access memory, and I do believe cache is our NAND gates or NAND kind of memory. But once we get to that chapter, I will myself refresh that, and you guys will refresh that, and we will talk about the type of memory, because it's basically, if I recall correctly, it's kind of like solid state memory a little bit, but you know, I'll put a rain check on that because I don't remember off the top of my head. But it is definitely faster than RAM memory, because RAM is very slow. I mean, figuratively, it's way faster than the hard drive, but it's very slow because first of all, you got to refresh it every millisecond, and then it takes time for it to actually read the data, because you have to work your way through the matrix of the RAM, because the RAM is like this matrix thing, and you got to work your way to the right cell and get that data, and all that takes time. And then the cache memory is just so much faster. So yeah, but yeah, basically that's what that is. And it's not just about the fact that the cache can hold. I mean, yes, there is one plus, I suppose. If it's smaller, you can seek faster through it. But it's also just about the type of memory being faster. And it's very expensive too. Like, it's the most kind of expensive memory you can have in the computer. Otherwise, we would just be making RAM out of the same memory as cache, and we'd be having fast computers, but much faster computers. But it's unfortunate, but no. So anyways, the L1 and L2 cache, the L1 is going to be the fastest, and the closest one, and then the L2 is a little further away. And again, we will talk more in detail about cache when we get to that chapter, but ultimately, the only thing I want to point out now is that you can see that there's an instruction and then there's data cache. What happens is this: if you see inside of the core here, maybe I can zoom in a little bit. Yeah. Inside of the core, you have your arithmetic and logic unit, ALU, but which does the processing of the data. So it might say something like load D word 5 or something, and then multiply it against this and that. Here's the thing: the instructions that it needs to go in the program, the sequentially, it's gonna preload them, or it's going to attempt to preload them ahead of time. Because here's the thing: you got your assembly program, which for now, let's just think in C++ terms, okay? Let's say that the first thing you need to do is you need to load a variable, and then you need to load another variable, and then you need to add them together and store the result, okay? This is always going to be the order that things run in, okay? Now, where is that information stored? That information is stored in my executable file. That executable file is stored in main memory. Well, actually, initially it's stored in the hard drive, but it gets loaded into main memory, right? Okay, so I'm going to look at the first instruction, which is to store into variable A, right? I got variables A and B. So I'm storing into A and B. L1 and L2 are not shared. Only L3 is shared because, as you can see here, this is an individual core, and then this is multiple cores, and then they get shared. So only L1 and L2. But that is up to the architects and the designers to kind of come up and figure out whether they want to share it or not. But this is what they found is the best case scenario, because sharing involves a lot of extra stuff, because as you saw, race condition and those kind of things. So you don't want an L1 to be shared, because then that it slows the computer down. But yeah, so you gotta get that instruction that says to create a variable and load information into it, and then create a variable, load information, and then load those two variables, add them together, and save the result in a different variable. So if you just wait and get every single instruction from main memory, you're like, get the instruction to load variable 1, get the instruction to load variable 2, there's going to be a gap between each instruction. Like, you're going to say load variable 1, okay, what's next? Let me go check in main memory. Slow. Oh, the next instruction is to load variable 2. Okay, do that. What's next? Slow. And so the computer tries to predict what's going to happen next. And in this case, it's very obvious because it's sequential stuff. So it's just going to load a chunk of the instructions to run, which again, this is assembly, but I'm thinking C++ terms, but assembly. It's going to load a chunk of the assembly that's going to go next, and then put it into what is the instruction cache. And that's kind of like the to-do list that is going to happen immediately. And why is it doing that? Because it will save it time when it comes time to actually to run these instructions, right? So it can be sort of like, if you ever been in a place where there's a line for something, and then they put a bunch of people in the next section. So maybe things like Disneyland. If you've been in the Twilight Tower of Terror or the Guardians of the Galaxy ride, you know, there's a line, but then they put them in an elevator, and then they bring them to another line. You know, the reason to have multiple sort of batches of lines is also to have people ready to go for the next elevator ride that comes, right? Or the next roller coaster that comes. And so that can be kind of your cache. You know, you're going to put those guys to be ready to get on. You know, usually all the rides actually at Disneyland that are like sitting based, you know, they've split you all into different lines. If there's a multi-row vehicle, like, you know, roller coaster or something, and they put you all in each row, and they tell you you're going to go here and here. They do that ahead of time, so that way when the next vehicle comes, they unload, and then you load in quickly, right? So that is so that you know, if you wait until those people unload, and then you go from the main line, and you're like, okay, you go to row 1, you go to row 2, you go to row 3, that slows things down, right? And the idea is you have tons of people that want to go on this ride, so you need to make the process of loading and unloading as quickly as possible so that you can speed up the amount of people that can go on the ride per hour, right? So same thing with the computer, actually. I don't know who came up first with the idea, computers or Disneyland, I don't know, but I'm pretty sure it was neither of them. So that is your instruction cache, essentially. Now, can anybody think of a problem with this idea of having instructions ahead of time? Like, what in programming is going to cause problems with the idea of trying to to kind of list the next instruction available? Like, what kind of programming concept is going to give us problems with this idea? Not race condition. That's unrelated, really. Something simpler than that. Functions. Yeah, there's something about functions, but there's even a simpler one than functions. But functions is definitely one of them. But with functions, you know when the function call happens. Like, you know, so you can then go and get the code from the function call. So there's something even simpler than that. Yes, it has to do with predicting the incorrect instruction. Jumps. Yeah, somebody said jumps. Okay, so what about jumps? So what instruction in C++ involves a jump in assembly? The most basic, simplest one. The one with if statements. There you go. Yes, there you go. If statements. That's right. Because what's the big hard thing about if statements? The big hard thing about if statements is when you get an if statement, it's going to compare in the most basic if statement. It's going to compare A and B. Okay, whatever A and B are. And depending on if they're greater than, less than, or equal to, or whatever, it's going to go either to the if clause or to the else clause, right? And so the computer has a problem there because it's like, who do I load? Do I load the if clause? Do I load the else clause? Do I load both? You know? And it could be completely different code bases to go either way. Like, there could be a billion lines of code inside the if statement. Don't do that. And then a billion lines of code inside the else clause. Or maybe there's an if, else, if, else, if, else, if. You know, you just do your... I did see this in 135 summer too. Somebody wrote an if statement that was over 1,000 lines of code. And there was about 100 different if-else clauses to it. Basically, I don't think they understood how to do ASCII math. And so they did an if statement for every single letter of the alphabet, uppercase and lowercase, I think. And then they had other if statements for like numbers and other ASCII. I don't know. I saved it somewhere because I was like, no. But it worked. The program compiled and ran. So that's kind of sad because I can't take points away. But yes, they're not a CS major, so I feel you know, that makes me feel better though. So otherwise, yeah. So yeah. So anyways, yeah. So that would be the worst nightmare actually for the computer course. It's like, oh my gosh, there's so many different options. Which one do I put in my instruction cache? And so that's a problem. That's a problem that we're actually going to spend like a chapter on at the very least. And that's called branch prediction. Because what happens is the computer tries to predict what is going to be chosen in the if statement. It's going to try to load maybe a couple of options if it can. But if there's so many, then it's going to predict. Now, what does it do to predict? Well, most code involves looping, right? And if it sees that you're in your looping, you keep picking if statement option 20 out of 50, then it's going to predict that you're going to pick that next. So it's very basic prediction based on previous stuff. It's not like machine learning tier or anything like that. We can't really implement that at this level because that would be slower as well. So it has to be a prediction that can happen quickly. And so basically, it's just going to try to see where you picked previously in that program. And if it's the first time that it's running it, then it's going to do what is known as a cache miss or a hit miss. I think hit miss or cache miss. In this case, they put it on the little chart that I showed you. They listed it as a branch mispredict, which means it predicted the wrong thing. Let me show you there. So that's the second one right there. This one. That is a branch mispredict. What that means is that the computer was trying to put instructions in the cache based on what it thought would be the smartest thing to do, because that's what it thought. Okay, this guy, it's in this statement, but more than likely they're going to this clause here, and it gets that wrong and needs to find it in the higher cache. In this case, the predict there is not even for going from like L2 to memory or L3 to memory. It's actually just going from L1 cache to L2 cache. So what ends up happening is it tries to look for something in L1, and if it's not there, it checks in L2. If it's not there, it checks L3. If it's not there, it goes to main memory. If it's not in main memory, then it checks in the hard drive. And if it's not in the hard drive, then I don't know what to tell you. So yeah, basically, more than likely it's going to be in main memory. But yeah, so that cache time missed is going to be wasted time because it has to kind of check that. And yes, it has to potentially look to the entire cache if you're not doing your cache intelligently and so on. So give this person 4 items to tell if it's an integer. Oof. I don't know. I mean, that class finished already, so I can't text it anymore. But before they did that, they had done a switch statement with like 30 different cases when they shouldn't have. So like I try to warn them, like no, don't do that kind of thing. But no, they committed. They went all the way. So yeah, I can't tell you who it is. I'll be doxing it, not a lot, but I can definitely pull up the code if I can find it and show you, because just removing the name, it's pretty interesting to see. You can see on Discord I was like crying about it. But anyways, the person passed the class, so they did good. They actually got an A actually in the class, which is oof. But at the same time, hey, good for them, They like I said, they're not TS persons, so even if they do bad if statements, actually that's much better than not knowing how to do if statements, which some people in that class couldn't figure out. So yeah, and it's dedication to actually code. The final program was like 1,800 lines of code, I think, when my solution was like 300 lines of code. So dedication to I guess they can't complain if it took 202 and the code, the number of lines of code goes up, right? Because at that point they're already writing 1,000 lines of codes and programs. So yeah, but anyways, so that's going to be your instruction cache, and basically it's trying to sort of queue things in the Disneyland ride to be ready to go. And if there's a branch, then it's going to be like, okay, I'm going to go and pick this one because I think that's what it's going to be. Maybe I'll also have the other ones in like the L2 cache ready to go just in case, if I can fit them all, and then just kind of go with that. And so that's what basically is happening on the left side here. On the right side with the data, it's kind of a similar situation. If you see the code load A and load B and then add them together, then you should have A and B ready to go. So and then you can just go and get them from L1. But you can actually run into the same issue with branching, because suppose that if you go in one side of the if statement, there's these variables that are going to be used. And then if you go on the else clause of the if statement, there's going to be other variables that are going to be used. So which one do you load? Maybe you can load both and you're okay. If you can load all the variables, you'd be good. But in a serious program, that's not possible because they're going to have thousands upon thousands of data. And you can't fit it all in even L3 cache with 15 megabytes. And so, and remember, you're not just working, because here's the thing. This core is not just working with a single program. More than likely, you are working with not just the program that you're running, your assignment, CS135 or 202 assignment or 302 assignment. That's not the only thing this guy's running. This guy's probably running like 50 other programs at the same time. And so those programs also require data to process. And that has to be in caches as well. So because of that, you know, it's the cache space is very valuable, and you can't just dedicate it to a single program. You know, right now in that cache, there's actually pictures of me in there, like because the cache has to predict, you know, like actually that's actually pretty interesting problem. You know, if I move my hand this way, you know, it needs to process that data and have it ready to go because it's going to the internet. So it's predicting that the next thing that it needs to load in there has to do with this specific program, WebEx, because that's one of the big flows of information. And it might actually even try to predict like which pixel is going to be updated. If I start moving my hand like this, it's eventually going to figure out that it needs to update the pixel ahead of time, and that it needs to pull that data. So it's going to load that data or something like that. So yeah, it's actually a very, very complicated process when you think about it, that it's not just running your program, it's running all of the programs of the entire computer. So there it becomes a very, very valuable asset of space. More code means better. Yeah, more code means better programming indeed. Yeah. How does cache prediction know it messed up? Well, when we get to cache, when we talk about the cache chapter, you will see, but essentially it's because it didn't find it. It looks for the instruction. Each instruction has a name to them associated, and or they have a number, like a line number, which is part of the program counter, and it basically doesn't find that number inside of the cache, and then it knows that it's not there. So then it goes to the next one, and then to the next one, until then to main memory. So yes, you know, it's basically like I'm looking for this variable name in the case of data, and it doesn't find it. Then it goes look in the L2 cache. If it doesn't find it, it goes up. So that's how it knows it's messed up. That's actually a simple part of it. So yeah. So anyways, now going back into the actual image of the chip. Let me. Okay. That's okay. That's good. You can see here that the L3 cache is right here. For data B and B. So I think one of those probably is instruction, and the other one is probably for data. Let me go ahead and take a look in the book. By the way, this is what is known as a printed circuit board, which is a rigid flat board that holds and interconnects chips and other. Oh wait, well actually technically PCB is actually not the chip itself, but the plastic that the chip is on. So like your motherboard, the plastic itself, that would be the PCB actually. So correction there. So that would be like the green things that you see here. Which again, for a computer we call motherboard. I think most of you know that, but if not, then some people say the definition is a system board. So let's see here. Yeah, the book picture is actually better because I don't like how they did the little dots in there. So okay, so if you look in the book, each of those little acronyms has a definition for all of them, especially for the next picture, because okay, this is for the entire processor or chip, but if you go and look at each individual core, then for example, IFB stands for instruction, fetch, and branch. So it says these two subunits contain 128 kilobyte instruction cache, branch prediction logic. So that's your logic to predict branch that I was talking about. Instruction fetching controls and buffers. The relative size of these subunits is the result of elaborate branch prediction design. So basically the IFB is going to be trying to figure out what the next instruction is going to be, to put it in there, or figure out which of those instructions it has to be as well. So like that's to do with the actual prediction itself. The LSU, which is in the center. Here we go in the center, right there. That one is the load store unit. That contains the data cache. Whereas the IFB also contains so inside of the IFB is your L1 instruction cache. Okay, inside of the LSU is your L1 data cache. And it also manages traffic between L1 and L2. So it needs to find a way to kind of, basically, the L2 is going to be the next things to ideally go into L1. So they're kind of ready to go. Or the backups as well. So yes. So IFB is, I guess to your question, how does the cache prediction know it messed up? I suppose the IFB knows. It just knows. No, it's because again it can't find it. But yeah. But that's the one that basically confirms and says I did not find the data in the L1. So I'm going to try an L2. Then we also have the ISU. That one is this one here, top center. That is called the instruction sequence unit. That determines the sequence in which instructions are executed. So again, that is just looking at the program and seeing line 1, line 2, line 3. In what is referenced to as a superscalar architecture. It enables out-of-order pipelining. So pipelining is another big word that we're going to spend a while on. In addition to having instructions ready to go, it wants to make sure that it maximizes the usage of the CPU. And so you kind of organize things differently. And that's all I'll say about pipelining, actually, because it's a pretty complicated topic that we will have to spend time on. I would say that's actually, between pipelining and memory addressing are the hardest things that I seem to recall being in this course. So we'll wait until we'll burn that bridge when we get there. So yeah. Okay. What else we have? IDU. That is okay next to the IFB here. That one is called the instruction decode unit. The IDU is from the IFU buffers. So where's the IFU? It's not shown there. I suppose that the IFU buffer is maybe on this one. I don't know. But anyways, what is it? So let's see. It is responsible for parsing and decoding all the operation codes. So your assembly codes, each operation like load and store have a specific number associated in binary associated to it, right? It's basically saying that it's going to figure out what that operation actually is. So like opcode 55 means to load, that kind of thing. In terms of test quizzes, do we need to know all these terms? Well, the test is open notes, so I guess if I really was hardcore and asked you what ISU stands for, you could look it up. But no, you're just going to be asked, at least for this chapter, you're going to be asked some general knowledge, like what is cache for? What's like the major difference between the different levels of cache? That kind of conceptual things, which is more of what I care about. Well, as a programmer, that's more of what's useful. It's not that useful to know all these little individual things, but at the same time, it's good to know, because you're not going to be designing this. That's the engineers' jobs, like EE people and CPE. Nah, CPE don't do anything. EE people, yeah. Okay, what else do we got in here? That's interesting to see. PC. That's going to be your core pervasive unit used for instrumentation and error collection. I don't know. Don't worry about that one. We have our FXU. That one is cool. That's the fixed point unit. Fixed point arithmetic operations. That's where those happen there. On the other hand, we have the BFU, which is not, well, we have the BFD there. That's maybe what they meant. It's a binary floating point that handles all the floating point operations. So basically, a lot of the CPU's cores have a floating point like calculator per se, and a normal arithmetic calculator, so like fixed stuff, so like integer stuff, right? However, nowadays when we got our GPUs, that is kind of offloaded into that. All the floating point stuff happens in the GPU usually. Or at least it can happen. You should do it. Okay, let's put it this way. The programmer decides that, actually. But if you're a good programmer, you would make it happen in the GPU. Otherwise, all our games would not work. Like, it would be pointless to have a GPU. And then L2D and L2I are going to be the L2 and L1 caches. L2 instruction and L2 data cache, which is not shown in that picture there, but that's what it would be if it was there. Okay, so anyways, this is interesting to see because when we talk about a little bit about like Moore's law and how these chips have become this small, it's very, you can see like these things have very weird shapes to them. I think these are actually the real shapes in the chip. And the reason why they got all the shapes like this is because they're trying to maximize the real estate in the silicon chip. And so that's why some of them are like curved and stuff. They're really trying to squish everything together here. So that's basically 1.2. 1.3. Von Neumann's we talked about already. We talked about ALU. Then we have this nasty picture here. I think this is talking about memory. I read this 2 days ago. I forgot a little bit. Yeah, okay, so it's talking about von Neumann's. Oh yeah, for this I was like, maybe we could actually show, I wanted to show you von Neumann's original paper. Let me try to find that. Von Neumann, he wrote this paper in 1945. And that's kind of the origin of the von Neumann diagram, okay? Probably on Wikipedia, it's probably cited if I go to the bottom. Here we go. Hold on. This one. Archive from the original PDF. Click here to download your attachment. That is not sketchy at all. Here we go. Oh no, this is not the paper. Oh, this is something else. This one might be. Yeah, this one might be. So here. This is the OG paper that von Neumann wrote in 1945 describing the von Neumann diagram. At least I think this one might be. So in the book, if you go to page 12, they talk about sort of the first 5 sort of important parts of what memory should do, right? And that's where that diagram comes from. And so if we go here, you know, every digital computing device contains certain relay-like elements with discrete equilibria. It's fancy. Principles governing the arithmetic logical operations. Consistent use of binary system. So it might be a good idea if you want to read this later, or at least browse it. There's a lot of things in the class that we will talk about, and this is actually where they came from. I wonder if he has a diagram, like a von Neumann style diagram. I don't know, but here, I will go ahead and share this link on Canvas so you guys can check it out. And then, yeah, because it's. I mean, might as well read the original thing instead of read the original source, right? Okay, so go ahead and read the first to 5th stuff in terms of what is required. But in summary, it says that it must have a arithmetic central part, so it needs to have some sort of math. It needs to have a logical control device, which is kind of like the control unit. The third one is it needs to be able to carry out complicated sequences, which means that it has to have memory. So that's going to be the third component, important one. And then your memory, which he compares actually to the associative neurons of the human nervous system. Then he goes ahead and says the I/O part, which are going to be the sensory and afferent, or motor and sensory neurons. Motor or efferent neurons, which are the sensory parts of the body, which are your I/O, so I guess like how you get input. And so he calls those the outside recording medium of the device. And he keeps using the word organ, which is rather interesting. And then he needs a way to transfer information between those sensory sort of parts, which is the I/O, and the control and associative neurons, which is the memory, which is kind of like your system bus, essentially. And then finally, also transferring for output, in this case, not just for input. But yeah, so it's kind of abstract, but go ahead and read it on your own. Now, as for what the diagram is, it's kind of saying the same thing. So the diagram is saying, you know, here we have our ALU, and here we have our control unit, and here we have our IO, and here we have our memory. Okay? And so basically it's saying you need to have an in and an out from the IO. And here you can see that it's coming into the arithmetic logic unit, both in and out, but it's going to the MBR. Now, what is MBR? Down here you can see all the acronym. That's your memory buffer register. So that's actually when you think about a buffer, like when you're coding, that's kind of what that is. Like, you know, you type something in the terminal and then it's stored in the buffer, which you can then read in with cin. That's kind of what that is. And same with when I don't know, if you're taking me for 202 and 302, I tell you, like, you need to flush your output because otherwise it may not print out if your program crashes. That's kind of what that is. So like if your program is supposed to send something down to the IO, like to the terminal output, it sends it to the buffer, which then at the time it finds right sends it to the output. But if your program crashes before it does this sending, then it's like, well, he's gone, so I don't need to send it anymore. And that's why sometimes when you run a program, it doesn't print something out before it crashes. So like I to R, R to C, I think that's what they have in the book, because they do use those weird letter acronyms. So let's see. Because they got 3 specific CA, CC, and C, and M, and I. So I think you're right with that arrowing. But I'll triple check. But anyways, back to this. The other sort of useful thing to know is that there's both in and out from main memory to the ALU. Again, going through the buffer. That is going to be sort of for reading in data from your program. However, there's also accessing to memory from the control unit. And that's because the control unit may have information it needs to get from memory. So basically or it needs to write some to memory as well. So that's as you can see, this is sort of the buffer is kind of like the middle ground. You know, it sends information down to both the ALUs, like control circuits here, arithmetic logic circuits, but it also sends it to the program control unit. So basically, this is a fancy version of what we've seen already before when we saw this thing here. You know, internal bus and control unit, ALU, and registers. That's kind of like the same thing. This is just how memory is connected to that. So take a look at this. You know, read what each of these registers does. You got your program counter, which is going to increase by 1 every instruction, I believe. And then you got your instruction register, which is going to hold the immediately next register that you're confirmed to be running. And then same with the instruction buffer register. That's the one above it per se. And this is actually before you even get to cache, because the caches, if there's caching, it's going to be in between here and here. That's kind of where the caching is going to really be, or it could also be here, I suppose. So now, what do instructions look like? Okay, so this is assembly stuff. I'm sure you guys kind of went over this in assembly, and I don't need to go too much in detail. But in the example that they give, they start talking about IAS, which stands for the first generation of computers use vacuum tubes, blah, blah, blah. For our purposes, it will be instructed to examine perhaps the most famous first generation computer, known as the IAS. The IAS computer is known as the stored program concept. So there's no actually definition of what IAS actually stands for, but oh well. Okay, what does IAS actually stand for? IAS computer. Advanced study? Well, that's the 2 letters, but what is the first letter? Institute for Advanced Study. There we go. That's actually another link itself. So here, I'll post that on you posted it too. Thank you. But here's the canvas. Here's the Wikipedia for that, so you can read about that institute. So, anyways, they created sort of the general purpose computer, and it was Von Neumann was part of the group, so it's sort of the first Von Neumann computer after he proposed it in 1945. Okay, so it took them what, like 6-7 years before they kind of came up with this, and that's kind of what this is. But most of our computers are going to come, at least home computers, are going to come from that sort of architecture and in general distribution. So inside of the IAS that they created, they decided to make the width of basically your memory and instructions to be 40 bits or 40 bits. So we got 20 and 20. And so what are the two things that you could store in memory? You could either store data or you can store the next instruction to run. And if it was an instruction, then you actually could store two instructions, a left instruction and a right instruction. And of that instruction, the first 8 bits, and each bit is just a 0 or a 1 binary, stored the operation code. So that's the instruction number, right? So like I said, operation 1 could be to load, operation 2 could be to store, operation 3 could be multiply, operation 4 could be divide, operation 5 add, and so on. Okay? And so 8 bits means that how many operations could you store in this machine? Well, what's 2 to the 8th? Then that kind of, maybe 2 to the 7th. What does that tell you? And that tells you the number of operations. So 64, 128, maybe. I don't know. I don't feel like doing math, so I'll just do the calculator. 256. Okay. So that would be if you could store all 8 bits, which you would be able to, I believe. On the other side, you have 12 bits for addressing. So that is addressing for other parts of memory. And so what is the biggest address that you could store? Well, that would be 2 to the 12th. 4,000 addresses potentially. And I think it also says here that they have a 4,000 address system. And so essentially, again, this is assembly stuff, so you guys should know that how this load things works. Even though I haven't done assembly in a while, I still remember that that's kind of how it is. You got to give it the address and you get it the operation code. And so that is what you would store. But the other thing you could also store is data. And for data, if you think back to just a basic integer, then you can just store it in binary and then convert it using basically the exponent here that we did, 2 to the dot power, and then you convert basically binary to decimal. However, if you want to be able to keep both positive or negative numbers, you reserve one of the bits to indicate whether it's positive or negative. So that's going to be your sign bit, and that's going to be the first one. So in this case, you could store one bit for positive or negative and 39 for the number itself. So that's actually bigger than what we normally have for integers, which would be 32. Well, 31 technically because of the sign bit. So that's even a bigger number. That's actually too many zeros to figure this out. It is 549 billion numbers that you could keep in this. So that's bigger than our usual, what is it, like 1 point something billion or 2.1 billion that you can store positive and negative because it's 4.2 total range. So yeah. So that's what kind of is with the memory format. And in the book, by the way, for the previous picture, they talk individually about each of those registers. Like MBR, they say, contains the word to be stored in memory or sent to the IO unit, whereas used to receive a word from memory. So you can go and read that more in detail, but I'm going to move on so that we don't run out of time here. And the one thing that I did notice when I was reading the book and then I looked at the PowerPoint is they don't have the table. But if you go on page 16 of the book, they have a table where they have the instructions that the computer had back then. And I don't think it's either on the other slides. Yeah, it's, oh no, it is, perfect, yes, nice, it is here, okay. So it wasn't on the figures, but it's on this. So, this again should be easy for you guys that you just took to a team, but the most basic instructions that they had in there was they had a load and a store, which is transferring contents from, for example, for load from this register into the accumulator, which is the one where you're going to actually be able to do math on. And then load is backwards of that. Jumping as your go-to statement. Then you have your conditional jumping, which is your if statement. And then you have your arithmetic op stuff like addition, subtraction, multiplication, and division. And yet again, even back then, they were doing the thing where they put the quotient in a different part of, or a different register. They put it in the MQ and they put the remainder in the accumulator. So even back then, they were doing the whole thing with like splitting the division into two different places, which, if I recall, still happens in x86 assembly, right? They put it in like the DAX versus EAX and all of that stuff. So yeah. And then they had some pointers technically with the address modify stuff. So even back then, they were pretty hardcore. So from there, by the way, I didn't quite say, but I kind of mentioned it, that von Neumann wrote this paper in 1945, and then they completed the computer in 1952, the IAS thing, and that back then they were using vacuum tubes. So yeah, I think I mentioned that, but just in case I didn't. So yeah. So now, is there any questions on von Neumann's like original machine? Or and yeah, that's a long time ago if you think about it. Like 1945, that's like World War II ending time. So by the way, I think this is in the book. It mentions how I think Alan Turing and von Neumann were both kind of coming up with the same design around the same time, but von Neumann kind of beat him to the punch on it. But it definitely was something that it wasn't just one person that came up with it, though. I would say it's more of a group of people, but they're the most famously recognized. It's a team effort, guys. Not quite. So the question was, has von Neumann's architecture been altered at all? Not quite, because we still use RAM, and then we have our CPU, and then we have our I/O devices. However, in the book it's mentioned that there's also what is known as Harvard. I'm actually glad you brought up. There's also Harvard architecture nowadays. So right now we're talking mostly about our general purpose home computers, or sometimes mainframe computers. But there's a big growing area of computing for what is, I think, section 1.6, which is embedded devices and ARM architecture and all of those things. And some of those have changed they're not following von Neumann's per se. For example, they may not have a memory to them. They might just have registers inside. They might just have like mini memory inside of the CPU and that kind of thing. And so one of those popular ones is called Harvard architecture, which is this one. In the Harvard architecture, this is just from Wikipedia. I literally just found it right now. Is you have your control unit, your ALU, but then you have your instruction memory, your data memory, and your I/O. And you can see there's no real RAM. Like, data memory is, I mean, it splits data and instructions. And normally with von Neumann's, they're both kept together in RAM. Here it's split, but this is all within the chip. Like it's not even it's not like different components entirely. It's all together, splashed together. And as you can see, modern uses of it, we got digital signal processors, and more importantly, this is what actually is mentioned in the book, is microcontrollers. So when we get to that section, we can talk more about Harvard architecture. But I would say that that's the one where it's / altered / different. Because I mean, it is a lot like von Neumann's, but it's not the purest version. So, yes. Sorry I missed. This is about... the answer was that we, if we want some wait when we get to cache, we may have more specific questions. But for now, we're just doing a quick overview. So if you get asked a question about cache, it's going to be more like, what is the purpose of cache? Like, what is an advantage of it? Those kind of questions. Not super specific right now, because I mean this is an overview right now of this. I mean the whole class is a lot of overview. You don't really go too much into detail. Pipelining you do. Okay, so the next section is talking about, we already kind of talked a little bit about transistors, but it's talking about gates and logic gates and how they're applied in computers. But as I said, I already kind of did talk about that. So there's not much that I can say about it other than Moore's law. Yeah, I can definitely talk about Moore's law. So last time I said that one of the ways that you can create RAM is you can use a flip-flop, and basically one signal switches it from read to write, and then you can store data in it, and that data persists until you basically cut the power. And that is achieved with silicon, with a transistor made out of silicon. And so back in the day, the original computers, and I think that's what they mentioned here, is a single self-isolated transistor is called a discrete component. And throughout the 1950s and 1960s, early electronic equipment was composed largely of discrete components. So you had individual transistors that were in like a breadboard per se, and that's what they did. But that's very expensive to manufacture, especially when you think about that we have billions of those nowadays. So eventually they said that's not good. We are going to sort of squish them all together into a silicon waffle. I think it's called waffle or waffler. So that we can have multiple ones together. And not only that, but because they are together, then the components to communicate between basically wiring per se is no longer really necessary if everything is together, or there's less of it needed. And so that was kind of the big like wow explosion moment for computing when we started doing that. Really, here's an example of a flip-flop that I was saying. So you have your read and write, and you have your input. If you have the read signal on, so that means you pass current through there, then it's going to store whatever the input is. And then when you turn that off, then you can change the input here, but it's not going to change what's stored here. If you turn write on here, then it's going to open this link and allow it to flow out. And yeah, and here's just a regular, like an AND gate, you know. You have an input, and then you turn it on and it flows the output. So you don't always keep it on per se. Transistors. So transistors, other than what it says, yes, they're fundamental blocks. And as I said, they were discrete components, so they were packaged separately and then soldered on. Okay, so if you open up like an old radio, you can see how things are like a resistor. We still use like resistors that we just solder on. You could do the same thing sort of with a transistor, but eventually we did the wafer. And so the wafer is you take this little piece of silicon, and then you create directly like laser engrave per se the transistors, and then you chop it up because you make multiple chips within one. And so here's the wafer. Each of those is a chip. Each of those has each of the little squares is a single gate that they create. And then all they do at the end is they add terminals per se, like little pins, so that you can feed in electricity and also signals in. So on one side of the chip, and then the other side is just metal, so that you can cool it. And then bam, you got a chip. And so the big breakthrough came in 1965. Yeah, 1965, when Gordon Moore. So I'm sure they have a thing on him here. Yeah, Gordon Moore, the co-founder of Intel, basically said like, "Yo guys, we just like did this amazing thing with chips that we can like use a wafer and like basically stamp transistors." And I predict that every year we are going to be able to double the amount of transistors that we can put in the chip, because we basically improve our miniaturization of this. Basically, you know, if right now we can stamp a 10 by 10 number of transistors into like a 1-inch chip, we can probably make a machine that is small enough that can stamp now 20 by 20 or something, or 10 by 20 or whatever like that. So he said we can put more chips in more transistors in the same space every year. And at the time, he said this, I think, just to kind of make money and sell Intel chips at the time. But it turned out to be true. Like his thing, for the most part, turned out to be true. Every year since 1965, yes, it did. It did slow down. I was going to get it's actually there on the side, but in the beginning, at least every year for the first 5 years, it was true. It was doubling the size of the number of transistors. Around the 1970s, the technology kind of hurdled a little bit, and it went from 12 months to 18 months, but it was still double. And a lot of the times between now and then, or at least now in 2005, people kept saying, oh, Moore's law is going to break, we're not going to achieve. But there was a breakthrough in technology every single time that allowed us to continue to follow his sort of law or prediction. And there's a second part to it, because there's two parts. One of the parts is that he says you're going to put the double number of transistors. But the other part, the important part, is he said the price will remain the same. because you're still using the same number of silicon per se. So, and that's true. The price has remained the same in computing. A computer cost 20 years ago $1,000 or $2,000, and it still costs $1,000 or $2,000. If anything, it has gone down, but the number of transistors has gone up. So the power of the computer has doubled itself, but the price has remained for the most part the same. That is the one of the, and the word very nicely in the book. It's one of the most amazing sort of breakthroughs in technology in our history. This growth in density is one of the most remarkable technological trends ever recorded, and I agree. That's insane. Like, think about it. Who gives you twice the number of stuff for the same price every year? Like, nobody does that. And Intel has done that. And that's why I like Intel. That's an Intel advertisement here. But yeah, so here's the thing though. Once we got to around 2005, we hit a bit of a roadblock because we were getting too small that we could not keep up. So Intel kind of predicted this. So whereas in the beginning, their development cycle was every 4 years, they would come up with a new, smaller architecture with a smaller, basically less distance between each transistor in the nanometers. Basically, they started to sort of instead of having like a 2-year development and 2-year production, they sort of how do you call it? Like, they put them on top of each other, so they overlapped. They overlapped the development and research phases. So that way, while they were developing the current technology, they were testing newer one, so that they allowed to compress this research time, and that's how they could continue to maintain Moore's laws. A better way of saying that they probably have here. Let's see, where they mentioned. They did mention that. I could have sworn because I read it. I don't know, but somewhere they basically mentioned that they switched their production speeds to basically split the R&D. They split the R from the D, and they overlapped them so that they could have a team working on the R while a team was working on the D. So like, if I discover how to do 8 nanometer chips right now, then next thing I do is I go on and move on to developing that. But while I'm developing what I just discovered, somebody's already working on how to get the 6 nanometer version working per se. That's what I mean essentially. So yeah, it's mentioned somewhere there, but I can't find it to me again. So yeah, I mean, you're reading the book, so you will find it. So when the CPU goes from 14 to 8, is that a leap in technology and making resistance smaller? Yes, but now we've reached a situation where, and I was saying this the other day, we have a real problem with Moore's law, because we're cheating at this point. We reached a situation where we could not go smaller because quantum tunneling and all these other weird effects that happen at that tiny size. I'm saying that the walls of the tubing per se, and the walls of the transistors, the gates themselves, they're actually, think of them as actual gates at that level of to stop the electrons from flowing. You have an AND gate, and if you don't have both things on, then the thing should be closed. Otherwise, it should open, right, and let electrons flow. And it's a semiconductor, so that's how semiconductors work. We had to make those gates so small. They're like, think of it, overgeneralization, but think of them as a 1 atom in width. Here's the thing: 1 atom should stop an electron, but quantum physics and quantum tunneling come into play, and the electron will actually phase through the wall. Like, it literally just goes through and keeps going. I'm sure you've seen this on like YouTube, that very popular example where they're playing pool, quantum pool, and sometimes the ball hits the other ball and bounces, and sometimes it just goes right through. I'm sure you've seen that example. Otherwise, I can find it on YouTube at some point and post it on Discord. But yeah, that's kind of the same that they have. So they have found a way to alleviate that for part of it, and they went a little bit smaller, but they had to find another way to throw in more transistors. So that's when the growth of multi-core chips came out. And so, yes, we are still doubling the number of transistors for the same price in a chip, but now we're actually mostly doing it by just putting more cores in the chip. which is kind of cheating because we are actually, they're becoming a little bit bigger per se, and we're not really going with the same space, but we're just doing this with more than one core. So it's a little bit of cheating Moore's law at this point, What is the issue? Do we have to go smaller? Yes. So that's a good question. And yes. So here's the thing. The other part of Moore's law is that when you go smaller, the reason why things become faster is because they're closer together and the electric signaling can go faster. It's actually, here. Let me zoom in. There's 4 things. We got the cost of computer logic and circuitry has fallen. But then the second one, the one you're talking about, the electrical path length is shortened. It's increasing operational speed. Also, because it's shortened and there's less basically distance between communication, the power and cooling requirements go down. And so if you just put more chips together and just spam them all, then your power and cooling go up in price because you got more heat generated out of this thing. There's more connections between them. Okay, and that's the thing. When you have multi-cores, then you end up having actually more connections, which is why we're kind of cheating on that. Also, technically, the computer becomes smaller. That's true, but then again, computers haven't really changed in size in the last 20 years. Although, yes, you're going to say, oh, a smartphone. Yeah, but that's kind of different-ish thing. But yeah, everything is closer, so there's less heat generated in general. And so if we just be like, okay, let's just make a chip that's like this big, yeah, you're going to have to cool that thing. And that cooling that thing, you're going to require like a car radiator size thing to cool it down. So that's one of the reasons that we got to keep it small, because otherwise it's just uncoolable at this point. In fact, one of the ways that we could speed up okay, so we can add more transistors to have more power, but we could also just make it faster by increasing the clock rate when we talk about clock rate. But that increases the heat exponentially. That is why for the last 20 or so years, maybe not 20 or so years, but the last 10 years, 10, 12 years, I don't know, I'm getting old to the point that things start merging together, but like, I think around the time that we got the first like 2 gigahertz processor was maybe 2000. Well, I don't even figure out because there's a table here, so I can probably look at that. But here, let me go on. Core 2 Duo, 2006. So 15 years. 15 years approximately. So that's when we kind of hit the gigahertz sort of clock rate limit. After that, if you go anywhere above 4 gigahertz, there's too much heat generated to the point that you need like insane cooling. And so if you notice, our gigahertz speeds haven't gone up since then. Like chips today are still running at 4 gigahertz or less. And it's very rare to see something around 5 even, because it just gets way too high. So there's so many different things that we can do to kind of double the power, and sort of follow and cheat into keeping Moore's law. But we're definitely hitting some limitations, but it's kind of like life finds a way. We have figured out ways to maintain sort of that technological increase, because it's it's an economy. We keep increasing the power, we keep the demand. The moment that we hit a wall and we can't make faster computers, Intel's going to go bankrupt, because no one's going to buy new computers, or like they're going to buy the same chips, but they're not going to be interested in upgrading anymore. Right now, if you play games, you buy a new GPU because eventually your old GPU is no longer going to be enough to play the latest games, because it's just going to be super low frame rate or just won't even work anymore. So you are compelled to buy a new GPU that has more power. Same with a CPU. Eventually your computer becomes slow, and the reason it becomes slow is because the programs require more power to run, and your computer is still using the power from like 5 years ago. So you buy a new computer. So it's an economy in the market. If all of a sudden it just stops, and now it's like 10 years from now we're still using the same power, then why should I upgrade? If I bought the best computer at that point, there's no point for me to upgrade, because nobody's going to have higher requirements for the programs, because then there won't be a market for it. So it's not just because we love science. It's because Intel loves money and they want to keep getting paid. So it's a win-win scenario, to be honest with you. There's a good example of capitalism that actually works. Hey, SpaceX and Intel. So yeah. So the electrons are facing through the gates because the gate is too small. It's more like the gate is, well, okay. Me trying to explain quantum physics and tunneling is not going to go really well. But it just happens that when the wall of the gates, there's too few atoms there. Sometimes, whether or not actually there's too many, okay. If you got an atom here and you got another atom here, normally they bounce, per se. It's not even touching. It's electromagnetic forces that stop it. But sometimes they phase through. But if you have a wall of like 20 things, it might phase through one, but it'll bounce off the rest of them. So the thicker your wall, the higher the chances are that it bounces. But if your wall is one atom thick and it phases through that, then it'll phase through everything, and then it screws up your logic. And bam, you got a bug. So the thinner the wall, the higher the chance that it's going to phase through the entire thing. That's kind of the oversimplification of that. But I mean, you got to get like a quantum, like a physics degree to understand some of that stuff. I don't understand some of that stuff, so I'll do my best to, because I do want to spend at least one day on quantum computing, because it's cool stuff. And this is a computer organization, and I think it will be unfair not to show you what the future might look like. So, well, no, they melt today. I mean, like, if you heard of people overclocking their computers and eventually melting their chips because they their cooling fails and they don't even have enough time to turn it off. Like, I have fried a chip before, so it's not theoretical in the future. That has happened before. Oh yeah, your thermal paste, like you have a bubble or something, and then bam, it fails. But yes, there are. It's somewhere in the book, I think, it might be on a chapter that we don't read, but some of the ways that they're trying to make things smaller is to find an alternative to silicon. And right now, I was having an argument with an EE person about this, because I said, hey, there's a lot of things that are like on the list, and he's basically like, yes, but none of them are useful for like practical purposes, like general computing. They're for special computing, and so we have not found a solution. Like, we have not, but I do think that we will find a solution. So, anyways, oh snap, we got 3 minutes of class. Let's see. The other thing I wanted to show you was this thing. So I think we can cover this real fast. This is just this is a really cool chart. By the way, what was this picture? Oh, this was just what the CPU looks like connected, and then that's fine, whatever. Oh, here's a good diagram of Moore's law. So the number of transistors, you can see here at 65. Now, this doesn't look like it's doubling because this is a logarithmic scale chart. So that's why it looks linear, but it's logarithmic. It's actually, it would be doubling. It would be like, this is dark, but like the best example of a logarithmic scale is just look at the coronavirus spread. If you look at it in normal scale, it goes like that because it doubles potentially. Whereas in a logarithmic, it just looks like a line. If it looks like a line like this, then it means it's doubling. But it's just easier to see in the logarithmic scale chart, okay? So you can see here in 65, Moore's law is promulgated. That means he basically just said it out loud, probably in a marketing meeting or something. And then you can see it's going up, up, up until pretty much now. And then in the book, they go over like the evolution of the Intels. So I don't know. We don't have enough time, but we'll go over it next time. But it's just for your own reference. Like, you can kind of see like the first computers in like the 70s. They had 2,000 transistors, and then in 72 you got about double that. In 74 you got 6,000, and then 78, look at that, 29. And then if you skip over to like, when I started playing with computers and stuff, it was around the time of Pentium. That's around I think my first computer was a Pentium. Like, no, my first computer that I remember, because we had like a 370, I think. First computer that I remember was, I think, a Pentium 2 or Pentium 3. It might have been a Pentium 3. Yeah, I think it was a Pentium 3. And then I also had a Pentium 4. And then I skipped the Core 2 Duo era, and I jumped into the I's, I think. I don't know. The computer that I have back there is old. I think I upgraded the chip to Core 2, but yeah. So we'll go over this chart next time. So anyways, for your readings, let's see. Right now we are basically at essentially 1.5. And so finish chapter 2. I'm sorry, no. Finish chapter 1 for tomorrow. And then from there, I really want to cover for Friday's TA session, which will be also on WebEx, unless he says otherwise. I want him to cover Andel's Law 2.3. So if necessary, we can skip to go to 2.3 for Friday. But for now, just finish reading chapter 1 and then maybe read 2.1. Okay? Finish reading chapter 1, which you should have, because I told you to read all the way to 1.6, and now you just got to read 1.7, and then read 2.1 as well. Okay? So that is what you can do. No, it's not just about a price. I don't think they've actually found a proper solution. So I don't think graphene is like the cure. That's the cure for all things. I think that's the one that I was arguing. I can't remember with my friend, and he said that only works for specific usages. I will have to find the Facebook chat and refresh my mind. He should come and talk one day if I can convince him, because he actually works on this stuff. So yeah. All right, any questions or anything? Otherwise, that's the end of this. I'm gonna save the chat. I'm still gonna write my script. I'll probably do it over the weekend, Python script, so that I can automatically, it'll download the chat, identify each person, and then add participation points to people that wrote in chat. So, yes. Cool. Yeah, go ahead. Yes. No, it's over the entire course of the class. Yep, all the way up to 2.1. Make sure you read up to 2.1. We may not get to 2.1, but I hope we do. If not, we'll get it on Friday. Your TA will talk something about it. Yep, cool. All right then, guys. Like I uploaded yesterday's video. I'll get this one uploaded as well, so that you have a copy. I forgot to hit record on WebEx itself, I think, but it'll be on YouTube, so you can refresh there if you missed something. So cool. All right then. Well, I'll see you guys tomorrow at 11:20 a.m. While I would love to have a class at night, I think right now we're set with the AM time. So yes. Bye, everybody. Thanks for watching.